Good day once again to the next lecture for Geotechnics 254. And today we will be looking at water flow through soil, and specifically the construction of flow nets to determine flow rates, etc. A bit of a philosophical statement. Knowledge is like a heap of sand. So to increase the level of the heap, you need to increase the base of the heap. So in a way, we started with this work already in engineering geology, now Geotechnics 254, and then next year in Geotechnics 354, you will work on the base of what you've learned so far. As I've said, we're going to look at flow nets today. It's in Craig 2.4, and at this point, I really want you to please go through the lecture or the work in the handbook as well. There's an example of making a flow net next to a sheet pile, and then I'm going to show the flow beneath structures such as dams, for instance. And then I also made available some internet material that is also very useful to understand flow nets. Flow nets look complicated and difficult in the beginning, but in general they're actually very easy and very useful. So very quick recap. I is the hydraulic gradient, so the total volume is the permeability times hydraulic gradient. K is the hydraulic conductivity. Q is the flow rate or discharge, and U the pore water pressure. In this particular drawing, I'm just showing how water could flow through soil. It's flowing diagonally from the bottom left to the top right in this case. And Vz is the velocity in the Z direction, and Vx is the velocity in the X direction. And delta Vx over dx times dx is the rate of change of the water flow speed. And you can calculate that for the X direction and the Z direction. In the conservation of mass theory, the flow rate out of the soil sample minus the flow rate in must be 0, because it's the change in volume over the change in time. It's a long mathematical expression which you can derive down to the next statement, statement 1, which says if you count the X and the Z together, you should get 0, conservation of mass. According to Darcy, the Vx becomes minus the hydraulic gradient times in the X direction, and the change in H over X, and the same in the Z direction. Just a quick statement, we use a minus value sign because we are losing head. We're not gaining head, of course, because the flow is impeded. And then Laplace came with an equation which basically says that the permeability coefficient in the X and the Z direction is similar or the same. And so the Laplace equation basically describes how the energy of a fluid changes as it flows and is independent of the actual permeability. And the Laplace equation is actually used in many other disciplines, not only in this particular case. The flow net itself is a graphical solution to the equation presented in the previous slide. So there's this long and difficult mathematical equation which we break down into a picture to make it more easy to understand. It depicts the seepage patterns beneath the structure, and it shows flow lines and equipotential lines. Flow lines can be can be seen as families of flow lines and equipotential lines, but these families or statements must obey the maps. What are the maps that we have? the change in, or the distance, delta H, is constant, and it's the total head over the number of equipotential lines. The change in flow rate is also constant, and that becomes the flow rate over the number of flow channels. Delta Q is KIA, as we've seen before, and that becomes K times delta H over delta N times delta S, where delta N is the distance between two flow lines and delta S is the distance between two equipotential lines. And we decide, it's almost arbitrarily, one can say that delta N and delta S is the same. And when you see the pictures, you will understand why I say this. So Q is delta Q times the number of flow lines equals K times the total head over the number of flow lines over the number of equipotential lines, and that is the flow. So ND, total number of equipotential lines, small nd is the number of potential lines from the chosen side. So the specific potential line that you choose at the point where you want to determine the flow rate. Then NF is the number of flow channels, the spaces between the flow lines, and H is the total difference in head. So for instance, determine the total head at ground surface, the datum. HA is 4 meters and HB is 0, and the head difference, total head difference, is 4 meters minus 0 equals 4 meters. So you set up the boundaries. Equipotential lines is the same as constant head lines, and you have an upper and lower flow boundary, and then you start drawing the equipotential and flow lines. These flow lines can never intersect the flow boundaries, and the flow lines and the equipotential lines should intersect at 90 degrees. And these lines are curvilinear, and therefore you should be able to draw a circle inside. So if we have the following picture of a dam, concrete dam, and there's the water right at the top of the dam at a height of 4 meters, and then the soil surface is 0.5 meters below the datum, which was chosen where the water will surface. And the 5 meters on the side depicts the depth of where we want to look. The dam wall is 8 meters long, and we want to see the point at the intersection of 3 meters into or from the left and 5 meters below the datum. I will show you the picture now, and then all of these will become a lot clearer than what I just stated. So delta H becomes the head loss between two equipotential lines, and delta N is the distance between two equipotentials. So delta H is the total head over the total number of equipotential drops, and delta Q is the same as the flow rate divided by the number of flow lines, and it's measured in cubic meters per second per meter. So this is the change in flow. According to Darcy's law, we begin with Q equals permeability times hydraulic gradient over the air times the area, and then we start changing, deriving the formula. We assume that the distance between the flow lines and the equipotential lines are the same, and we end up with this statement of Q is equal to permeability times total head over the specific flow line that you're looking at over the total number of equipotential lines measured in cubic meters per second per meter. HP is ND over total ND times H, and we normally work from right to left, so we start with the on the right hand side of the dam, and then we walk towards or work towards the point that we want to determine our flow rate. So this is the flow net. As I've said, the water on this side of the dam is at a height of 4 meters. Here there's 0.5 meters. Sorry, this doesn't look very nice, but it's 0.5 meters over here. So we have a HB of 0 and an ND of 0. And then we start normally, you start drawing from here. So the dam wall is the flow boundary, and the other flow boundary is here at the bottom, probably hard rock. You'd start drawing your lines more or less equally distant apart, and the aim is to draw a square in which you can draw a circle. Now this is not perfect, this flow net that I've drawn here, but for instance, in this particular case, you can still draw a circle in here, but it should actually be more like a curvier linear square. This is the drop delta H as you go through, as the water flows. Delta S is this distance between the flow lines, and delta N is the distance between the equipotential lines, and we say delta S and delta N is the same. And we eventually want to know what is the pore water pressure U at this particular point. Pore water pressure at point A, which is 5 meters below the surface and 3 meters from this flow boundary. So you draw your equipotential lines. It's your choice how far you want to draw them apart. The thing is, if you make it too small, it becomes very difficult to draw and you can lose track of the counting. And if you draw them too far apart, then you don't have nice squarish areas. It's very difficult to actually make a huge mistake with the flow net, and you will not lose marks, for instance, for drawing something like this. But this is typically how you would draw the flow net. And then you will also have your flow lines drawn as to how the water would actually physically flow underneath the dam, and this is very typical. And in this case then the total number of flow lines is 6. 1, 2, 3, 4, 5, 6. The bottom one is also a flow channel. And the equipotential lines, you start counting from this side: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the total number is 14, and this is the ND for number 14, and this is ND 0. So what is the pore water pressure at that point? The HP pore water pressure is equal to the specific the specific block that you're looking at over the total number of equipotential lines times the total head, and that becomes, in this part, basically you have the pressure plus the depth. So the flow, the total head. Come on, why is it doing this to me? So by substituting and changing the values as we got it, so at HA is equal to 0 plus 7.5 meters. The number of the flow ND is 7.5 meters over the total number ND, which is 14. So this particular one is 1, 2, 3, 4, 5, 6, 7, 1, 2, come on. 1, 2, 3, 4, 5, 6, 7.5. That's where that 7.5 comes from, and that gives you the energy head at point UA is 2.14 meters. Z is minus 5 meters below surface. So the pore water pressure is the unit weight of water times the energy head minus Z, and that gives you the pore water pressure is 71.4 kilonewton per square meter. So the ND in this case, the number of equipotential line from where you start counting. We normally start counting at the right. So 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7.5 over the total number, which is 14. Again, I really do urge you to please read the handbook and also look at the video that I provided. It sounds a bit complicated, but you need to work through this in order to make it your own. As I say, we are going to use the Flownets a couple of times in the next few lectures, and you can be sure that there will be a question on this in the test and exam. Thank you very much for listening.